What we're looking at here is a composite picture from Earth, taken from Earth. These are all real pictures here, looking towards the center of our galaxy. And this is ostensibly like if you looked up in the sky and somebody says, "Oh, I see the Milky Way," this is what they would be talking about. This is just kind of a stretched out picture of it a little bit that's gotten put together. And hopefully there's some things that kind of strike you as we look at this picture. Certainly you can see the yellow glow, but you can also see these dark filaments and clouds, these dark clouds that are in front of everything. And this is stuff that's just blocking light. And very broadly, whenever we talk about the interstellar medium, we're talking about all this extra stuff that's within our galaxy, within our solar system, within the regions of space that are not actually clumped up into stars or planets or something that we can give some other name to. So these are very broad collections of dust, and this is what it would look like in visible light. Now, if we look at other wavelengths, for instance, right here I am looking just at hydrogen alpha, so the brighter spots, the spots that are more white, indicate that there's more emission coming just from hydrogen. So the idea here is you see some very, very specific, really dark spots where there is a whole lot of hydrogen alpha emission. Some of these are nebula that we'll talk about. And then you see some of these kind of diffuse regions, these gas bubbles that are just massive areas where there is a lot of energy. These are hot regions where hydrogen alpha is actually being emitted. This is all places where we can get hot enough hydrogen to show off. Now, if we go down a little bit more just to radio, we can see that kind of our radio emission is spread throughout the galaxy. So again, this is the picture of our galaxy, but if I look in radio wavelengths, we find this really, really thin band kind of that makes up our galaxy. If I go back to the visible wavelength really quick, you can see how it's kind of thick. We've got kind of maybe a third of the width of the image, but when I look at it in radio, it looks almost smaller. Certainly there's a little bit of gas and dust otherwise, but it's got this really thin line across it. Now, as we talk about the interstellar medium components and the different types of interstellar medium, we're basically picking out these different features. Now, don't necessarily need to worry about tying them too closely to this, other than all of these observations we can look at in this context as well. Whenever we talk about a very hot region, we're talking about something maybe that I can see in X-rays, one of these kind of clouds that are here, but there's really not much X-ray in the center region. And some of these are just artifacts. Some of these really kind of looks like somebody took a gash to it or a cat scratched or something. Like these are just artifacts of the observations. But in X-ray, we can certainly see that there's some really big, dark, or very bright areas here that have a lot of X-ray emission. Inevitably, these are almost all supernova remnants, as we'll see. And so these are all very intense regions of emission that are different, that we don't necessarily see in visible light. So let's get to it and look at the different components of the interstellar medium. Now I'm going to call out 4 specific types of interstellar medium, and these are just classifications, and we can get into nuances, and there's a million different ways to classify them, but this is the most common way to kind of look at the interstellar medium. And then, of course, we'll talk about cosmic dust and its influence on what we see as well. So for the most part, we'll look at these regions and we'll characterize them. We're going to look at temperature, the composition of them, what are they actually made of? Are they emitting or are they mostly absorbing light? So whenever we talk about the absorption or emission, we're talking kind of absorption or emission of light here. And then finally, maybe there's some specifics about where or what they are, and so we'll get into there more so on the where and kind of what we really closely associate with them is in the notes here. So the first region we're going to look at are called H2 regions, that is Roman numeral 2. And the Roman numeral 2 indicates that it is ionized hydrogen. So your book discusses this as well, and we say that H1 regions are maybe neutral hydrogen regions where there's no ionization. So the Roman numeral 1 means it's the kind of main species of hydrogen that's not ionized yet. Whereas H2, we've got singly ionized hydrogen, and this continues on with more and more elements. So maybe oxygen 5 actually is ionized 4 times. So we kind of subtract 1 from the number, and that's how many times it's ionized. Just the convention that's used here. But here with our H2 regions, these are hot regions. We're looking at 10,000s of Kelvin. This is kind of what we'll say is hot interstellar-wise. These are enough to ionize hydrogen pretty regularly. There's a lot of ultraviolet light that's actually given off in these regions as well. And what happens is the ultraviolet light gets absorbed by the hydrogen, and then the hydrogen tends to emit off because we can absorb ultraviolet light very readily and then kind of take a couple of steps down as the electron goes down to its ground state, and it'll give off a lot of visible light. So the picture that's here is the Orion Nebula. You can actually see this. You can even see the colors through maybe a small set of binoculars, especially in the winter. A small set of binoculars or a small telescope, you can see some of these brilliant colors with your own eye. It's a pretty dominant region when you can find it in the kind of scabbard of Orion there. And this ionized region gives off a whole lot of light. Now, there is more than just ionized hydrogen in here. We can see things like oxygen and nitrogen. Other things get a little bit ionized, or at least they're excited within this region very, very well. So we can make out those as well. The pinkish color in this picture, very specifically, that kind of pink hue that dominates the color is the hydrogen. That's what color hydrogen looks like if we just kind of zap it a little bit. And so these regions are associated with spectral emission lines. Sometimes they're just called emission nebula because they're giving off light kind of inherently. They need a source of energy. They need to get some ultraviolet or other wavelengths of light, but then the nebula themselves glow, and that's how we see them. And these regions are usually by very, very hot stars, and are usually associated with what we call star-forming regions. So the Orion Nebula is actually kind of a stellar nursery. It's actually where new stars is formed, and we'll get into that in the next chapter. But these are regions that are by very hot stars, because these hot stars emit a lot of ultraviolet light. Remember, as the things get hotter, they emit shorter wavelength light, and to the point where some of the hottest stars, some of the 20,000 Kelvin stars, really start to emit most of their light in ultraviolet, and they cause the gas around them to glow. And since these were regions where stars were recently formed, there's a lot of material, a lot of gas there. So they're moderately dense, so they tend to glow fairly brightly here. And so these are our H2 regions, and they're characterized by really having a lot of spectral emission lines. And this is very contrary to the next type, which are wherever we have neutral gas or cool gas. Kind of call these just neutral hydrogen clouds or neutral hydrogen gas. They're kind of on the cooler side of things. They're below star temperature. So one of the things that we'll kind of say is, we kind of refer to the coldest stars as kind of being warm in an interstellar sense. So the 1,000 Kelvin or so is starting to get into kind of the warm range. It's not quite a star temperature yet, but it's warm to us for sure, and kind of cool, not quite cold interstellar wise, but 100 to 1,000 Kelvin or so. These are clouds that are just neutral gas. There's really not enough temperature there to ionize them. Not enough energy bouncing around. So they're characterized by what we call an absorption spectra. So as we look through this cloud of gas, some of the light just gets blocked. Some of the light gets absorbed by the molecules in there, and it'll glow very dimly, but they're usually not dense enough, and there's not enough light passing through them that we really see any glow from them, though they're far more associated with what we call absorption spectra. But the one place they do kind of glow, so at the start of the video I showed you that very, very narrow band in radio, just that really thin stripe in the radio picture of the sky that showed up, and this is what we call the 21 centimeter emission line. And this is actually these neutral gas clouds tend to be fairly bright actually in radio, or at least in this very specific band. This is associated with not electrons changing energy states or changing orbits, but they can we call it spin flip. So basically the electron turns upside down, or it changes the direction that the electron is spinning. And this emits a very, very low energy photon, and this photon is associated with a 21 centimeter wavelength and is visible in radio. And this is the most common kind of gas. This gas is basically everywhere. It's pretty ubiquitous. So in our galaxy or many other regions, these neutral hydrogen gas clumps are kind of the default, if you want to think of it. And they just have this absorption features where they block part of the light. Now, back onto another type of emission nebula, we can even get hotter than our H2 regions, and so your book coins these as just being ultra-hot gas. And most of these regions are from supernova remnants, so this is not just a star or a couple of stars or a cluster of stars that are heating up a region. This was a star that exploded, and all that energy is still making its way through the interstellar medium. So all that energy, all that temperature from a star exploding, and we'll talk about these in more detail later, is making its way through all of this gas, and it glows visibly. There's supernova remnants that are nice to look at visibly. This is actually the Vela complex, so there is the filaments there in the center are kind of part of the Vela supernova remnant. This is actually a very large structure on the sky. It's actually somewhat hard to actually image because it's so large on the sky. It's pretty dominant in there. And so we have these filaments and all these big chunks of ionized gas that are there, and these are kind of characterized because the gas is so hot that you start to get totally ionized things like oxygen and nitrogen and heavier elements that were formed in this explosion. So you start to get these other elements that are popping up, and so these are often dominated not by hydrogen. It's almost too hot for hydrogen even to form lines. So we get some of the heavier elements lines that become a little bit more dominant here. And because of their temperature, they also have strong emission in X-ray and in gamma rays. So actually my study was very much on studying these supernova remnants and gamma ray emissions. So this is my personal field of study, is looking at these guys. But they have very strong X-ray emission, and that's how most of them get discovered initially. And so this X-ray emission is a thermal X-ray emission. They are giving off all those X-rays because they're that hot. Remember, we have hot stars that give off ultraviolet, and the next step up the temperature scale and the photon energy scale is X-rays. So these guys are so hot that they're giving off more than just a star's temperature. And we'll spend a little more time looking at supernova remnants when we look at the death of stars. So we'll look at these more particularly, but just as far as gas goes, these are sometimes big, hot, dominant structures. You could see some of those in the X-ray picture that I showed you. Now again, the whiplash back to something very cold here. These are molecular clouds. Now this is Barnard 68. This is, your book talks about it in terms of dust. But this is a molecular cloud, and it's or a dark nebula, sometimes they're called, because they block just about all light. They're very cold, and they have all neutral gas molecules, dust, and the absorption in here is very wideband. It's blocking nearly all light in most wavelengths, even outside the visible. They do tend to glow a little bit in infrared or maybe radio. You can see them a little bit better, but they tend to have pretty wide band absorption. There's a lot of dust and just stuff kind of blocking there. And these are what I will term here as pre-star formation regions. These are regions that they're starting to cool down, and as dust clouds like this cool, they actually tend to get more dense. And as they get more dense, they'll eventually start heating up to the point where we can form some stars. But they gotta get really dense first. And that's our topic for next chapter. We'll see kind of the evolution of these molecular clouds into an H2 region, if you want to think of it that way. That's kind of the evolution of some of these. So these clouds don't sit like this forever, of course. They're kind of ebbing and flowing, and this is just what we see of them as at this point. But these molecular clouds, they're very cold, and it's all neutral gas, molecules, and dust. Now, we call out dust specifically because there is another effect that dust does. Whenever we talk about absorption here with any of the clouds, absorption or emission here, I'm usually talking about them in the sense of where a photon is hitting an atom and it's moving an electron, or that electron is moving down to a ground state and it's giving off light. And if you need review on that, that's what we talked about in chapter 5. But that's when we have just single molecules or single pieces of gas. There is also large bits out there, and we coin these guys as cosmic dust. And this cosmic dust isn't necessarily, it's not like we just have cosmic dust regions necessarily. These are usually, there's cosmic dust that is part of dark nebula and neutral nebula, the neutral hydrogen region. So they're generally found in the cooler areas. And so this dust adds another effect onto the emission or absorption spectra. And these are usually very large molecules. They can just be a very large molecules like the buckyballs, or sometimes they're even small ice grains. So they're actually, they started to form something a little more substantive. I mean, you can think of them like space snowflakes if you want, or space hail sometimes, but they're very, very small, very fine. And this has an effect of what we call reddening and scattering. So if we look through the cloud, so if we have our dust cloud there, where there's a bunch of cosmic dust in it, and we're looking at a star through this dust cloud, the star will appear to be missing its blue light. It will see basically just the red light, but the blue light is mostly missing. And so this reddening effect, where we're missing some of the blue light, is something that is characteristic of these dust size, because they tend to select what colors kind of more broadly than an emission line. So when we talk about atomic emission lines, are usually very, very small. Cosmic dust tends to kind of affect a whole range of wavelengths. So usually they tend to select and kind of let the red stuff through, but they let blue and the shorter wavelengths tend to get scattered. So we talk about reddening and scattering. And again, these pieces of dust, they can be part of molecular clouds or neutral regions. They as long as it's relatively cool, they can be there. And so if we look, I've got the picture here of Barnard 68 again there on the right, and then the Pleiades in the upper part. And there is some idea here that these could just be a matter of perspective. So the Pleiades, you can almost see this type of structure with your naked eye. You can see some of the blue glow. You get out to a dark spot, it's a pretty dominant kind of blue region. And perhaps to another observer, if the stars are on the other side of those clouds, so the stars there in the Pleiades, almost all those stars are actually closer to us than the cloud. So from the other side of that cloud, an observer could see the Pleiades stars as being more red. It's actually removing some of the red light, whereas what we're seeing is just the scattered light. The scattered light can bounce straight back at us or come to us at an angle, and so it's thought that these stars are kind of a little bit in the foreground, and we're seeing the reflection off of that nebula. So sometimes we talk about the Pleiades being a reflection nebula because it needs another source, and we're just seeing the kind of bounce off of it. Whereas like Barnard 68 here, that little clump there, this is an infrared picture of it. It's not perfectly apt here, but just seeing kind of the red hue of it as we look straight through some of the stars that are there. You can certainly see that the stars coming through, only getting the red parts, all the blue parts are basically totally missing there. And so it's just a matter of perspective here, whether we see an absorption spectra or whether we see this reflection. On another note here too, this is actually how why our sky is blue. Our sky is basically acting as one big reflection nebula, so we get all the wavelengths of the sun, comes in, hits our atmosphere. The blue light gets scattered from the nitrogen and oxygen molecules in the atmosphere, scatter blue light, kind of just like the molecules would in the cosmic dust, and it scatters the blue light, only lets through the more red components, or in our case, kind of yellowish red. That's why the sun, if we go into space, appears pretty white. But when we get into our atmosphere, you think of some kids drawing a sun on a piece of paper. They always use something like yellow, and that's just because that's the only colors that make it pretty much straight through in our atmosphere. All the blue light that would be coming from our sun makes the sky glow that pretty blue, and these nebula are the same exact process there.